Right, so the first thing I want to do is I've posted your next problem set, and that's this tradition. Let me figure out how to share the screen here. Say a couple words about the next homework set. It is yeah, so this is I'm pretending this one's due on the 23rd. So as I sort of promised, this is kind of a sweeping up details kind of thing. Let R be a commutative ring, commutative, but for most of this problem, perhaps without identity, maybe it doesn't have it. Let S and R be a multiplicatively closed subset. Of course, you can say that doesn't mean zero, but maybe I'll allow that here. I want to define on the set R cross S the equivalence relation. The order pair RS with R and R and S and S is equivalent to the order pair R prime S prime, if and only if there exists an S double prime in S such that S double prime times this is basically the cross multiple, right? So is equal to zero. Notice in a more familiar environment, so for example, with integral domains, this would mean that RS prime equals R prime S, right? But this is a more general thing. Show that that little tilde there is an equivalence relation, A. B, show that the set of equivalence classes, and I will denote the equivalence class by the suggestive fraction form R over S. So the set of equivalence classes forms a commutative ring with identity. So now we get one. So that's kind of the group. One of the group of things is even if R doesn't have an identity, this construction will pick up an identity. With multiplication, with addition to multiplication given respectively, like we've seen before. And number three, if R has an identity, then show there is a one-to-one correspondence between prime ideals of R that exclude S. And of course, I mean that the prime ideal P intersect S is empty, and the prime ideals of R localize S. And just kind of for your own interests here, the reason I assume identity here is because I wanted to be sort of well defined what I mean by prime ideal upstairs, right? Because if you remember, sometimes if you don't have identity, you might have things that don't have maximal ideals. Number two, and two will actually two is useful unto itself, but it will also probably be useful for problem three. Show that the domain R is a principal ideal domain if and only if every prime ideal is principal. This is very similar. Y'all remember that theorem we did about R is Noetherian if and only if every prime ideal is finitely generated. This is kind of a ripoff on this. And this actually shows you the principle is important as well, because again, what this says is R is a PID if and only if all you got to do is check the prime ideals. If they're all principal, you're good to go. It's a PID. Now, let me introduce this terminology here. If R is a commutative ring with identity, we said the chain of proper prime ideals, fancy P0 inside fancy P1, all the way up to the N, has length N. Notice we start counting at 0. We define the Kroll dimension of R to be the supremum over all lengths of chains of prime ideals that you can find. So you look at all possible chains of properly ascending chain of primes, and you take the supremum over all those. This is called the Kroll dimension. In a certain sense, this is a very popular sort of measure of size of a ring, right? It's basically how high can you stack your prime ideal, right? 3. Let R be an integral domain, P an overring of R. Show that R is a principal ideal domain if and only if R is a UFD and the Kroll dimension of R is less than or equal to 1. Right? How many of you already knew from a previous algebra class that any PID is a UFD? Right, that's an oldie but a goodie, right? Well, this is the one that ties up the converse. What do you need plus UFD to get PID? You need precisely that condition. You can only stack your prime ideals so high. Right? Show that if R is a UFD, then any localization of R is a UFD. So this you might be able to use actually one on this problem as well, or localization kind of stuff on this. And finally, show that if R is a PID, then T is a localization. That is to say, any overring of PID is a localization. We talked about an example the other day in class that in general this is true. In fact, it's not even true for UFDs. Even two-dimensional UFDs, you expect there to be overrings that aren't localizations. Okay, any questions on that? All right. Well, hopefully you'll have some fun with this. Okay. So, now we move on to the next chapter, which we're going to talk about some basic ring extensions that is natural rings, maybe a ring to start with, and homomorphisms. So let's get busy with the homomorphisms. Okay, so I think everybody's familiar with this, but we'll make this complete. Definition 2, 1, 1. Let R and S be rings. The function we call phi from R to S is a homomorphism of rings. So there's all kinds of homomorphisms, right? Division groups, modules. So basically, this first one says, hey, this is a homomorphism of abelian groups. That's it. A ring is first and foremost a abelian group. It's got that underlying structure, and this basically says it's a homomorphism of a group. And it respects the multiplication. So there's a number of adjectives, modifiers that can apply to this. I might say injective or a monomorphism. I might say surjective or an epimorphism. I can have a ring isomorphism. Unless otherwise stated, unless I tell you specifically otherwise, we also see by default that if R and S have identity, then they see identity. Yeah. We will assume that. So unless I tell you otherwise. By the way, how many of you have ever seen this convention, right? Sometimes in the beginning algebra course, you don't mention it. You just say, okay, here's a homomorphism. How many of you have ever seen the caveat that, okay, I'm going to assume one, right? Does it puzzle you? First time I ever saw it, it puzzled me. It's like, why are you going to demand this sort of thing? And so I've got a little proposition for you that I think sort of justifies why somebody would make this assumption in the first place. Proposition. Let's let phi from R to S is a ring homomorphism. And well, let's see what one is R has identity. I mean, after all, if you're not going to assume, don't assume they have identity, what are you even talking about? If R has identity, and this is a ring homomorphism, if S is a domain, then so if you have a ring with identity and your codomain is in fact an integral domain, then that's not an assumption anymore. You have to go there. So proof. So suppose the phi of one goes, it has to go somewhere over in S. A squared is phi of 1R, phi of 1R, which is phi of 1R squared, which is phi of 1R equals A. I forgot to put that word in there. That's rather important. Yes, of course, I want this to be a non-zero ring homomorphism. You've always got the zero homomorphism, don't you? You want to throw that rule out. So we have A squared equals A, and you probably know where this is all going now, because now you have A, that's A minus 1, is equal to 0. Of course, A minus 1 makes sense because S is an integral domain, so it has to have a 1. Therefore, A equals 0 or A equals 1. If A equals 0, then for all R and R, phi of R equals phi of 1 times R equals phi of 1 phi of R equals 0. So A, which is phi of 1, is equal to. So in other words, if you assume that the homomorphism is not 0 and your codomain is an integral domain, then you've got no choice but to take identity to identity. Okay. Definition. Come on, S, the homomorphism. We say the image of phi is the set of phi R and the kernel phi set of X and R to X. You see So this gives rise to the familiar first isomorphism theorem. Theorem 214. If you have a ring homomorphism, then the image of thing in S is a segment. And kernel and R is an ideal. So the image is a subring, the kernel is actually of S, and the kernel is an ideal of R, and R, like that ideal, is isomorphic to B. This is really the only isomorphism theorem that I talk about in this course. I assume that this is kind of review for you all. But the first isomorphism theorem is sort of the daddy Mac, right? Because every other isomorphism theorem follows from it essentially. And the most important being sort of the lattice, the most important, I think, sort of corollary is the lattice isomorphism theorem. Basically says that if you have, well, I'll understand that in a minute. So, notice that curve phi in R is something. All right, so I'm going to take us back to group theory. We already know that the kernel of phi is actually the kernel of, because remember, that ring homomorphism is first and foremost group homomorphism, right? So this is a subgroup, and X is in the kernel of phi, then phi Rx is phi of R, phi of X, 0. Therefore, curve phi in R is ideal. And without proof, I'll say that the image of the thing in S is a subring. That follows immediately from the fact this is a homomorphism. You already know that the image is a subgroup of S, right, from earlier group theory. And basically all you need now is closed-ended multiplication, which follows from the fact that this is homomorphism. Everybody okay with that? So this is one of these theorems where if you had to rebuild this every time, this is a huge pain in the keystone, right? Because how are you going to get an isomorphism from here to here? It's obnoxious, right? Because what you have is these are cosets. So we're going to go through this once to kind of set everything right. So let's do the isomorphism. Let pitchfork from R mod kernel phi of the image of phi. And we'll have to find this function now. So what am I going to do? Am I going to do R plus curve phi? This is kind of a good, even though you all may have seen this in one form or another, this is kind of good because it illustrates my favorite points about math. Don't do it if it ain't easy. All right. What's the most natural way that I can get from this stupid looking coset into something in the image of phi using this tool? Well, I am a simple-minded fellow. So I'm going to use my tool and I'm going to plug in that stupid representative. And I'm going to cross my fingers that this works. Right? what's the first thing I gotta worry about? Working well. Yeah, is it well defined, right? And that's why this is a big theorem, because it usually saves you a lot of work because it's doing stuff. In fact, the only time that you say, actually, the universal mapping property, the tensor product, that probably say the most work of all. But anyway, we need to show this as well. So we need this to be a function. So let's let x plus kernel of p equal y. So let's pick two representatives out of the same coset. This of course means x minus y. And this is synonymous, the same. P of x minus y must be 0, because after all, x minus y is in the kernel of p. And this is by the way, I did run the glib, we pull that sign out, but it's easy to verify phi of minus y is minus y. Right? In fact, that's an old group theory things. Therefore, p of x p of y, therefore pitchfork of x plus kernel of p is equal to pitchfork of y. So and so let me point out, of course, that the fact that phi is onto is easy because the theorem says image of phi, and of course you can cover anything just by picking the right coset, right? So the onto part is easy. Yes, suppose next plus kernel of phi is contained in kernel. Well, what this means is pitchfork of x plus kernel of phi. Well, my rule says this is phi of x. But this is also should be 0, right? Because of the fact that this is in that x plus kernel phi is in the kernel of this portion. Therefore, x is in the kernel of phi. So x plus kernel phi equals 0 phi and this form. That's just but let me also point out, I guess, that one of the big things that you can improve from the third osmosis theorem follows this. There is one-to-one correspondence between ideals, or in fact prime ideals, of R containing I. Here, R is commutative ring with identity, and I is some ideal in it. There's a one-to-one correspondence between ideals of R containing I and ideals of R mod. So you can add the adjective prime or not. So not only to the pair, not only to the ideal pair, also some primes as well. Okay. Any questions so far? Okay, so that's a bit about homomorphisms. I'm going to do, let's do some ring extensions. And I'm going to start by talking about polynomials a bit. And I'm going to do this backwards. There's a couple ways to do this. But I'm going to do something a little bit strange. Some people start off with polynomials as the basic notion, which is a natural thing to do. And then they get the power series. In the beginning out, of course, often what you do is you start with a polynomial and you get the power series, but you say, just let them go on forever. This is just formal symbolism. You get like really fancy. In some context, you might say, okay, look at this completion, right? And you do a structure, complete power series. That way, I'm actually going to start in the other direction, just like you might start with direct product or direct sum. I'm going to begin by defining power series rings first. Definition. So this is the analog, sort of starting with direct product and then getting the direct sum out of it. Let R be a ring. The power series ring. Or power x is given by, it's just this collection of formal sums. Right, and we just treat this sort of symbols. That's it. These are just big, formal, infinite sums. It's just a notation, right? It's the analyst that screws all about trying to plug crap in, right? I mean, that's where they made their mistake. Of course, there is one thing you can always plug into this power series. What's that? You always plug in zero, couldn't you? And in fact, that's a homomorphism. So. So, now I did say this is a ring, so I'm going to say, operations. Okay, the addition is just terminal terms. Exactly what you expect. You just compare, even though I haven't defined degree yet, you just compare the same degree terms, go for it. And multiplication. Sum. Times sum well, if this is going to be a ring, it better be a power series that comes out. But I'm going to tell you what the rule of C is. So So in other words, you kind of do this, this graded thing. Right, like C0 is just product of two constant terms. C1 will be the linear term B1 times A0 plus A1 times B0. Square term, this is more complicated as you go up. But at every step, this is a finite sum, right? And so I've timed the problem. Right, okay. Polynomial ring is something. Consisting of finite. Under the same, and when I say subring, I mean, of course, the same addition multiplication. So that is Rx is the set finite sums. Here we have one, 10. All right. So we need some observations. R, Rx, Rx. So, I mean, it's worthwhile noting that. Also, if R is commutative, respectively, has identity, then so if Rx and Rx. And notice that the identity of both polynomial and power series ring agree with what the identity of R is. Okay. By the way, you might think about why this is true for a moment. If you've got a polynomial ring in one variable, then you can certainly have a polynomial ring in two variables, right? So well, so now this is a ring, isn't it? Right? So you can do this. You can take a polynomial variable from this is some other variable, and this is what it becomes Rxy. And so you can keep going, and you can do any number of variables you want. Or you can actually do even uncountable. Here's the thing, right? I mean, you could have a polynomial ring over a field, say an uncountably many variables. Maybe you index the variables. There's one variable for each positive real number. Right? You have a variable thing. Now, what is a typical element going to look like? A typical element is going to look like it came out of a finite, because a typical element is still going to be a finite sum. And then any finite sum, you're only going to use, even though you've got uncountably many variables at your disposal, you only use finite many at a time. Right? It's kind of a neat thing. You can't do the same thing with power series. In fact, it is a question, what does it mean to be a power series and infinitely many variables? And there are at least 3 different ways to define this in literature, right? At least it's a more difficult question. You might think about why that is. Polynomials passing to infinitely many variables is a smooth process. Power series, at least trifurcates into, okay, now what we mean by power series, many variables. Let me, can anybody think of a quick sort of point of why things might be different than polynomial? Well, you can think of a polynomial ring as the union of all the subpolynomial rings, right? And it's all the same concept, right? Because remember, even if we use countably many variables, any single polynomial comes out of a collection of finitely many variables that we call, right? It's impossible to see, no matter how many variables you got in a polynomial ring, it's impossible to see infinitely many of those in one element. Right? Now, one thing that you could do is you could define power series and implement two variables as follows. Power series x1 in variable x1, power series variable x2, and take a union. Right? Well, that union, that ascending union, power series in x, power x1, power series x1, x2, power series x1, x1, x2, etc., etc. When you take the union of that and make that in a ring, then you're never going to see a power series that contains more than finitely many of those variables, right? Because since it comes out of the union, it came out of one of those steps in the union, which only involves finitely many variables, right? But you could define power series another way and have something like this. Right? That thing seems like another way to define power series, but it's not in the union, that nested union, because that one actually lives, that one actually requires infinitely many variables for me to be able to write it down. Right? So that's just one of the problems. So you might think about that. Fine. It is a very natural question. So here's a big question. Suppose R has a really sexy property, something really nice. And I can think of a lot of these problems. Maybe R is Noetherian. Maybe R is new factorization domain. Maybe R is integral closed. There's lots of nice problems. So is this nice property shared in the extension? Sometimes yes, sometimes no. So let me ask you, what do you think? R is a UFD. Still a UFD? Not here, not necessarily. Right. Yes, no. How about this? R is local. Never. The polynomial ring is never local. R is local. Always. Integrally closed. Yes. Sometimes. I think it also has to be completely integrally closed. Yeah. So it's there's strange things that happen. R is Noetherian. Yes. Hilbert Basis Theorem. And yes. So Noetherian is really nice regard to this. Oh, here's another one. R is finite dimensional. So I just talked about Kroll dimension, right, in the homework, how high you can stack your polynomials. If you start if you can only stack these in tall, then in Rx, worst case scenario, 2n plus 1. Right? So for example, if you can stack yours four high, if R is a four-dimensional domain, then the worst you can do in Rx is 9. It's dimension 9 or less. For power series, there are examples of zero-dimensional domains where you can stack primes uncountable power. Right? It's very bad. But let's do that really good one that I was getting all juiced up about was the Noetherian actually works for both. If R is a theory, I don't think I'm going to prove this quite yet because I want to channelize the rule something first. If R is commutative with 1, so we're going to assume that R is commutative with identity. I bring this up, actually, I make this distinction here because it can be an interesting converse. If R is commutative 1, if R is Noetherian, and so is Rs. Right? This is called famously Hilbert Basis Theorem. You might think about another proof. And I want you to think about it for the following reason. Here is another partial converse. And this is going to go over. Yeah. Rx is the theorem. Then R is the theorem. By the way, my blanket assumption here is just community. If Rx is the theorem, R is the theorem of the point. So the statement Rx is Noetherian implies that the ring has an identity, right? So in other words, if R has no identity, and non-zero, then Rx is different Noetherian. I find that interesting because the assumption that Rx is material forces you to have a form. That's kind of weird, isn't it? So for example, here is one of the simplest rings that I can think of that has no identity, right? That's not zero, right? And that is actually, I can make it worse. I can even make this finite ring. Alternatively, of the three two elements for the addition and multiplication of mod 4. This has no identity because it's got 0 and then 2 is a nilpotent, right? If you look at polynomial rings of both of these because they're non-zero ring, they're not zero ring. They have no identity. Anybody see what the problem is? And I illustrate this because let me ask you this: how many of you have seen the proof of the Hilbert Basis Theorem? Well, maybe we should do that, but there's some point in there. There's a subtlety that you might miss in that. I think like Hungerford's got kind of a standard proof. We can go over proof maybe next time. But I want you to think about this. If you look at the standard proof in Hungerford, somewhere in there, it better be the case, no matter how subtle it is, that the fact that R has an identity must be being used. See if you can look at that proof. And actually, this might help. So can anybody see? I don't know, an ascending chain of ideals or an ideal that can't be found in general. I'll wait, maybe my students have. So let's look at this one. Look at this idea. Anybody justify why this is not finally generated to see what this is on? Yes.
Because normally you be able to generate all the powers of x with x, but now because that only has coefficients that are nilpotent, you're not going to be able to do that.
There is no x right, in this ring because this ring here it looks like there's x, but really if you look at the definition of polynomial ring, it's just all formal sums. There is no x because there's no one to kiss up against the x, right? So the only things that can multiply x and be in that ring is 0 or 2 bar, right? And that's it. So look at this ideal, right? If it's finitely generated, then I is 2 bar x, 2 bar x squared, 2 bar x. That's equivalent to the ascending chain. There must be some point where I've picked up all the generated. Now, is 2 bar actually, this is how we use these things to manipulate, right? Because let me point out what happens if you multiply 2 bar by any non-zero element in this ring. What do you? That's right. Every day, this is a bloodbath, right? I mean, everything multiplies each other dead, right? So the only way that this can be in here is for this to be a sum of some of these generators, and it's clearly not, right? So this isn't even finitely generated, right? So there is no x, right? If this had an identity in it, then this would have x in it, and this ideal would be generated by 2 bar, because then the x is in R, and you get all these other elements. But here there's a subtlety. So look at your favorite proof of the Hilbert basis. And we'll talk about that a little next time. Any questions? All right, well, hope that was fun. Hope you all have a good one, and if nothing else, I'll see you by Wednesday.